Hi everyone, we are back with part two of the lecture on correlation and regression. So, why care about correlations? First, they can help us to develop a good measure for research. Any measure, whether it's a depression questionnaire, a personality test, a memory test, whatever it might be, it should be reliable and valid. A reliable test is a test that produces stable, consistent results. You can think of this as hitting the same spot on a target over and over again. If you gave someone a questionnaire and received wildly different results each time they filled it out, it's not a very good test. So, to test if something is reliable, we can use correlations and see if previous scores correlate to current scores. Valid scores refer to whether a test measures what it is intended to measure. You can think about this as hitting the bullseye of a target. Say you're developing a new intelligence test and include the question, do you like apples? Someone can answer yes all day long, making it a reliable test. But if it's not measuring intelligence, it's not a valid question. One way we can test validity is with correlation, where we see if scores correlate with related behaviors. For instance, we might predict that those with high intelligence have higher grade point averages. We can correlate that measure with the scores from our test to establish validity. We can also use correlations to make predictions. While it's not a crystal ball that allows us to see perfectly into the future, if two variables are related, we can use one variable to make predictions about another. For instance, there's a correlation between ACT scores and college GPA. Again, while it's not a perfect correlation, we can take the score someone obtains on the ACT and then predict how well they'll do in college. And lastly, we can use correlations for theory verification. If we theorize that two variables are related, we can test that theory through correlation. Maybe you think that the bigger someone is, the larger their limbs will be. You can test that theory by correlating two variables, such as height and shoe size, and see if that theory holds up. When it comes to interpreting correlations, it's really important to be aware that correlation does not equal causation. This means that one variable is not causing another. There is simply overlap there. One issue with correlations is the third variable problem, where an unmeasured third variable is actually causing the change. For instance, there's a correlation between ice cream sales and sunburns. But we know that ice cream isn't causing sunburns, right? There's a third variable of the sun leading to both ice cream sales and burns increasing. Likewise, there's a correlation between the number of serious crimes and the number of churches in a town. But the churches aren't causing the crime rate to increase. Rather, there's a third variable here of population size, where as population increases, the crime rate increases along with the number of churches built. We also have to be aware of the third variable problem, where correlations cannot tell us which variable is influencing the relation. Is A causing B or is B causing A? Take this example of books and reading. You can tell that this is hypothetical data because it's a perfect correlation, but for the sake of this example, say there's a correlation between hours spent reading and number of books owned. Do people spend more time reading when more books are available to them? Or do they buy more books when they spend more time reading? A correlation can't answer this question. We also have to be aware of spurious correlations, where there is no real relation among the variables. The overlap is just by chance. This is real data here that you can read about, showing a strong correlation between the popularity of the name Kenzie and UFO sightings in South Dakota. However, it's highly unlikely that naming a child Kenzie increases UFO sightings. Going back to measurements, we have to make sure we're getting the full range of scores to see possible correlations. When we don't have enough scores to see a relation, this is called a restriction of range. Using this example, say we take a sample of 10 people. This is highlighted using the circle on the right side of the graph. It looks like there's no relation here, right? But if you were to sample more people with a wider range of scores, there's a clear relation among variables. So we have to make sure we have a wide range of data. Outliers can also affect a correlation. Looking at this example, we have 5 scores that are all within a small distance from each other. The R value is a negative 0.08, so very low and probably not statistically significant, meaning that this variation is due to chance. But say you sample one more person and they're an extreme outlier. This person has a score of X of 14 and a Y of 12. Look at how that changes the form of the data and now suggests that there's a stronger correlation. There are different ways of handling this issue, but for this class, just be aware that correlations are sensitive to outliers. Going a bit further with the strength of the relation, looking at how close R is to 1 and -1 allows us to know some about the strength of the relation. But a better measure is the squared R, which allows us to determine the amount of variability that's accounted for in one variable by the other. When you square R, it essentially looks at the amount of overlap between two variables. Finding the R squared value is straightforward. You just take the R value from the correlation you ran and then you square it. Using the example from part 1 of the lecture, the correlation between hours slept and mood was 0.853. So 0.853 squared is 0.728. Interpreting this number, this means that 72.8% of the variability in mood is explained by hours slept. Here's an example for you to try on your own. In part 1 of the lecture, we found that the correlation between marital satisfaction and hours worked overtime is negative 0.859. What is the R squared value and the interpretation of this number? The answer will be shown in 5 seconds. Taking negative 0.859 and squaring it, we get positive 0.738. The interpretation of this is that 73.8% of the variability in marital satisfaction is explained by hours worked overtime. Another really important part of correlations is determining whether or not they are statistically significant. We'll talk in depth about statistical significance in future lectures, so we'll keep it simple for now. Statistical significance is the likelihood of the outcome being due to chance. Essentially, do we have a correlation due to sampling error, or is there a real relation here? We measure statistical significance using a p-value, which tells us the likelihood of that outcome being due to chance. So if we have a p-value of 0.05, that tells us there is a 5% chance that the results are due to sampling error. In psychological research, we want our p-values to be below 0.05. So if you have a correlation that is less than or equal to 0.05, great, you have a significant correlation. If it's anything over 0.05, not great. This is too high of a chance of error, and you can reject it and say that it is not statistically significant. You can think of statistical significance as a normal distribution with probability on the y-axis and all possible results on the x-axis. As you have learned, all likely observations are in the middle of a normal distribution. This means that unlikely observations are in the tail. The 0.05 cutoff is essentially how much of the tail are we allowing the scores to fall into. But what if you're expecting a specific outcome with your correlation? Say you're specifically hypothesizing that there's a positive relation among variables. This means that you're hypothesizing your score would fall into one specific tail of the distribution. We would call this a one-tailed test. but you might not have a specific hypothesis. Maybe you're only interested in whether or not the outcome is significant, and it's okay if it falls into either tail of the distribution. In this case, you would have a two-tailed test. Hang on to that because we'll come back to it. Before we can determine the statistical significance of a correlation, we need to understand degrees of freedom. Degrees of freedom are the total number of observations minus the number of constraints or parameters estimated. You can think about this as the amount of change that can happen without breaking the rules of a calculation. Different tests will have different degrees of freedom. For correlation, the degrees of freedom is n minus 2. So if you had a sample of 24, 24 minus 2 is 22. So your degrees of freedom is 22. With statistical significance and degrees of freedom in mind, here is an image of the correlation table posted to Canvas. The table is called the critical values for the Pearson correlation. A critical value is just how large your R value needs to be for the correlation to be deemed significant. In the first part of the table, we have the level of significance for a one-tailed test. So if you are looking for a specific outcome, positive or negative, and you want it to be at 0.05 or below, you would use the 0.05 column here. The next part of the table shows p-values for a two-tailed test. Note that the columns here are different and that the column for a p of less than or equal to 0.05 is listed right here. And lastly, we have degrees of freedom in the far left column. The table here is like the unit normal table, where it does not matter if the R value is positive or negative, because we're only looking at probability. So if the number is negative, we treat it like a positive. Let's do some practice with this. Is a one-tailed test with 2 degrees of freedom and an R value of 0.91 significant when our p-value is set to 0.05? First, we find the column for 0.05, we go down to the degrees of freedom, which is 2, and look at the critical R value, which is 0.9. We have an R of 0.91, so this is greater than the critical R, and therefore the correlation is significant. On the next example, we have a two-tailed test with 10 degrees of freedom and an R of 0.512. Selecting the column for 0.05 for a two-tailed test and identifying 10 degrees of freedom, we would need an R of at least 0.576. So this correlation is not significant. For the last example, we are looking at a two-tailed test with 12 degrees of freedom and an R of negative 0.65. Staying in the same column, but going to the row with the correct degrees of freedom, we need an R of at least 0.532. And remember that we treat negatives as if they were positives. So 0.65 is greater, and this correlation is indeed significant. In the last part of this lecture, we are going to talk about regression, or the trend lines you sometimes see in scatter plots. We use these lines for a few reasons. First, it helps to make the relation among variables easier to see. This example on the slide shows a strong correlation between GPA and SAT scores, and the trend line here helps you to see that it is a positive correlation. It also helps us to identify the center or average of the relation, which is what the dotted line shows. But most importantly, it helps us to make predictions about the data. So how do we calculate a regression to make a regression line and therefore make predictions about scores? In algebra, you may have used the equation y equals mx plus b to find the slope-intercept of a line. In statistics, we use a similar equation but with a different notation. We use y hat equals bx plus a, where y hat is the predicted y value, b is the slope of the line, and x is any given score. A is the y-intercept, which is where the line intercepts with the y-axis. To calculate a regression, we just plug in the pieces of information into the regression equation. However, to do that, we need to know what the slope and y-intercept is. You calculate the slope using the equation b equals r times sy divided by sx, where r is a Pearson correlation, sy is a standard deviation for y-scores, and sx is a standard deviation for x-scores. The y-intercept is calculated using the equation a equals my minus b times mx, where my is the mean of y, b is a slope, and mx is the mean of x. So putting this together, there are 5 steps to calculating a regression. You need to find the correlation, then you find the slope, and remember that the slope requires knowledge of how to calculate a standard deviation, so make sure to review Chapter 4 if needed. Once you have the slope, you can find the y-intercept. Then you can create your regression equation and plug in any values to make predictions. Let's bring back that example from part 1, examining hours slept and mood. This is just that bottom row of our table with the calculations we have already done together. In step 1, we calculate the R value. This has already been done and is highlighted in red at the top of the screen. So we can skip to step 2, finding the slope. To find the slope, we need to find the standard deviation for x and y. We have the sum of squares from when we were calculating the R value, so we are already part of the way there. Here's a shorthand equation for finding the sample standard deviation. Again, if you are not comfortable with finding the standard deviation, you need to go back and review Chapter 4 to make sure you understand this concept. The standard deviation for x is about 1.789, and for y, it's about 2.098. So taking that slope equation, we just multiply the R value of 0.853 by 2.098 divided by 1.789, and that gives us 1 approximately. From here, we can find the y-intercept. We take the y-intercept equation and plug in our numbers using the slope we calculated and the data from the table. The slope is 1, the mean of x is 7, and the mean of y is 4. So 4 minus 1 times 7 is negative 3. From here, we can create the regression equation. The equation is y hat equals bx plus a. So plugging in our values, we have a 1x plus negative 3, which is just 1x minus 3. From here, we can plug in any x values given. So if someone had 9 hours of sleep last night, what would we expect their mood to be, given that happiness is measured on a 10-point scale? Taking that equation, we just plug in 9 for x and solve. 9 minus 3 is 6, so we would predict that this person would be about a 6 on the happiness scale. Here's a practice problem for you to try on your own using the other example from part 1 with marital satisfaction and hours worked overtime. Find the slope and the y-intercept. The answer will be shown in 5 seconds. So for the slope, the standard deviation of x is about 2.981, and the standard deviation for y is about 7.18. So plugging that in to the slope formula, we have negative 0.859 times 7.18 divided by 2.981, which is about negative 2.069. So for the y-intercept, we plug that into the equation and we get 9 minus negative 2.069 times 6, which is about 21.414. From here, go ahead and solve for steps 3 and 4. So make the regression equation and then answer the following question. If someone's marital satisfaction score was 7, what would you expect the hours worked overtime to be? Pause to solve. The answer will be shown in 5 seconds. Okay, so the equation here, we take the numbers from the last slide, and we have negative 2.069x plus 21.414. And then we just plug 7 into the equation, which gives us 6.931 hours worked overtime. And that is all I have for you. I know that this chapter had a lot of information, so please be sure to let me know if you have any questions.